This meeting is being recorded.
Okay, let's go to the quiz. So on the screen up here, I have the quiz on the right-hand side and a little blank spot on the left-hand side where I can write out some notes about things. And problem number 1, let H perceptron be the perceptron hypothesis class and H stump be the decision stump hypothesis class. If K is a breakpoint for H stump, then K is guaranteed to be a breakpoint for H perceptron as well. The first important thing to observe here, and important thing that will be a trend in most of these problems and many problems from now on in the future, is observing when a hypothesis class is a subset of another hypothesis class. And here we have that, I will write it vertically so we have some more space for other things. H stump is a subset of the perceptron hypothesis class. Perceptron hypothesis class. And the reason for this, I think covered this in class before, but the perceptron hyperplanes anywhere in the space, the stump hyperplanes that are only perpendicular to an axis. So every stump hypothesis can be realized by some perceptron hypothesis, but not vice versa. And because of this relationship right here, we know that starting with stump, if K is a breakpoint for H stump, then there is there's no data set of size K that can be shattered by H stump. No data set of size K that can be shattered by H stump. But the perceptron being a larger hypothesis class, it could potentially shatter things that the stump hypothesis class might not shatter, not guaranteed to, but it could shatter things, and in many situations it will shatter things that are not part of the H stump hypothesis class. And so this direction right here is false as written. The thing that would be true is that if something is a big breakpoint for the perceptron, if something is a breakpoint for the larger thing, that means that the larger thing right here cannot shatter any data set of that size. And so the smaller thing also would not be able to shatter any data set of that size. So if the order of stump and perceptron here were reversed, if we were talking about a breakpoint for perceptron and checking to see is that also a breakpoint for stump, then it would be true. But in this case, with this direction, it is false. Other important subset relations here for these hypothesis classes is H stump is a superset of the H axis 2, and that is also a superset of H axis. And so all of this arguments about breakpoints, it's only dependent on the superset subset relationship, nothing particular about stump or perceptron here. And so a similar argument would hold for any of these hypothesis classes if they were being compared. Let's Okay, while we're talking too about here, it's also worth pointing out that the VC dimensions of all of these things, that the subset relationship here implies a number of important things for us. One of those is about the breakpoint here. Another one is about the VC dimension. So we know that the VC dimension of the larger things must be at least the VC dimension of the smaller things. And one of the things that we talked about in class was actually talking about these VC dimensions. And here for the perceptron, we had D, and for all the other ones, log D. I'm not going to write the asymptotic notation out here, but all of this stuff in asymptotic big O or big theta notation right here. And so because all of these three things here have the same VC dimension, their generalization error as predicted by VC theories all going to be the same. And so from a generalization perspective, there is no major difference between these three hypothesis classes right here. There's never an advantage for the generalization error of picking one of these over another. There could be advantages for other reasons like computational or for in-sample error. One of the relationships that we know so far is that the in-sample error of a larger hypothesis class is going to be smaller than the in-sample error of a smaller hypothesis class. And so the in-sample error of h-stump here is guaranteed to be at least as small as h-axis 2. And so h-stump is from a statistical perspective, more capable hypothesis class than h-axis 2. And so it's a much more popular one. In practice, people use h-stump very regularly. People very rarely use h-axis 2 because h-stump is just all around better. Okay, problem number 2 over here. Question, yes?
I don't know if this is a valid question, but we have h-stump with polynomial feature map of like degree, whatever, 2 and above. Can we conclude that like if k is a breakpoint for that, then it's also guaranteed to be a breakpoint for each section?
Yeah, so this is a good follow-up question here. It ties us into number 2 here, what we're going to be talking about. So I'll say some stuff and then I'll repeat the question. The problem number 2 here about this HV2, HV4 hypothesis class. And these are the perceptron with the 2nd and 4th degree polynomials. One thing that we know is that the H for the, HV sub I, that is going to be a subset of HV sub J whenever if I is less than or equal to J. And that's what one of the things that we went over in the notes packet about the polynomial feature map here. And this is the only relationship that we know about the subset inclusion relationship between that involves this feature map. And in particular, one thing that we do not know and is not necessarily true in general, it is not necessarily the case that h-stump is a subset of, say, HV sub I. That's not necessarily the case. The VC dimension over here for the h-stump, VC dimension, DVC is very small. And the VC dimension over here, DVC, is very large. But you cannot just compare the VC dimensions to determine the subset relationship. It is true that the subset relationship does imply things about the VC dimension, but the VC dimension does not imply things about the subset relationship. So in general, we're going to have a series of families of hypothesis classes where comparisons can be made inside of those families. So here's one family going axis 2 to stump to perceptron. Here's another family with the perceptron as the base hypothesis class and the feature maps as creating the family of classes where the family is parameterized by how big the feature map is. And then another subsequent family, which will be related to problem 3, is also HV sub I being a subset of HV sub J. But now with this V being the PCA. And the relationship here also holds about I, this is if I is less than or equal to J. And at this point, these are the 3 families of relationships that we've covered. And you can't say, in general, anything between these families, but only within the family itself. Does that answer your question?
Two questions. One is that in the second class of families, isn't H perceptron to be like the lowest member, right? Because wouldn't its feature map just be 1, like it's the original, so it's a subset of perceptron with higher degrees. And
yeah.
So if you have that, then can't you like combine the first one and the second one?
Yes. So this is a great observation here that if if we're using the perceptron hypothesis class with the polynomial feature map right here, and the polynomial feature map has degree 1, then those 2 families sort of stack together right here. When I wrote this as the not subset relationship, I was thinking this is not necessarily perceptron. This can be any for any H with this feature map, this is not guaranteed to hold. But if this is the perceptron, as it is written in the problem over here in part 2, then it would be a subset relationship, and you can glue those two families together. In general, for any particular hypothesis class, you might not be able to glue those two families together. So for one situation that's came up in the practice problems is if H here is the hypothesis class of the concentric circles, then you would not be able to glue this family together with the perceptron up above. But if it is the perceptron, so if the base class here matches the sort of the tail end of the class up here, then you can glue them together. The key thing, though, to realize, or one of the key things, many key things, one of the key things is that the subset relationship implies the VC dimension, but the VC dimension does not imply the subset relationship. I saw another hand out of the corner of my eye somewhere. So problem 2 right here, we have the subset relationship between HV2 and HV4. The subset relationship implies a relationship on EN, but it implies that the larger class has the smaller in-sample error. And here, HV4 is the larger class, and so it should have the smaller in-sample error. So this is false as written. It would be true if the inequality was reversed, if we said greater than or equal to instead of less than or equal to, because the subset, the larger class, has the smaller in-sample error. Problem number 3. So here, the subset relationship, again, holds from HV2 as a subset of HV4, and so I'll write it out down here, HV2 subset HV4, that implies the DVC of HV2 is less than or equal to the DVC of HV4. And our generalization error, as predicted by VC theory, is proportional to the square root of the VC dimension here. And so the class with the smaller VC dimension is going to have the smaller generalization error. And the question here is saying the generalization error of GV2 will be less than the generalization error of GV4. Again, GV2 is the smaller VC dimension, so it has the smaller generalization error. And so number 3 right here is true. Number 4. So VC theory predicts that when using the H-axis 2 hypothesis class, centering your data points results in a better generalization error with high probability. Key observation here on number 4 is centering has no effect on the VC dimension. And so no effect on the generalization error. As predicted by VC theory. So here we were, the question is stating that there will be an effect, but there is no effect, and so it should be false. In general, centering, the only way that it can help is on your in-sample error or your computational performance. It's never going to help on your generalization error. So this is a very common thing to do, but not a common thing to help your generalization error. Yes.
Wouldn't it be very likely that generalization error will get worse after centering?
Question is, would it be likely that the generalization error gets worse after centering? And the answer is that in expectation, it stays the same because the VC dimension stays the same. And so there's that whole probabilistic aspect of it, of the with probability, at least 1 minus delta, all of this stuff. And so when you do the centering, you are changing things. So the randomness can kick into effect in a different way. But if you ignore that randomness, just take what's going to happen on average, then no effect. Everything stays the same. Yeah.
And the statement's true for any.
Question is this statement true for any hypothesis class? And I could come up with a toy example hypothesis class where this statement is not true, but any sort of reasonable hypothesis class, anyone that we have seen so far, this statement is true. Yes.
Sorry, just back to my original question.
Sure.
If the H stump had a feature map, like a polynomial feature map, does that break the subset relationship with perceptron? Without?
Yeah. So this is a good question here. So the question is back up on our subset relations between all of the stuff in blue up here and the stuff in red down here. We said that if the stuff in red, the base hypothesis class down here is the perceptron, then because this matches the perceptron up here, we could glue them together. And the new question is, what if our base hypothesis class down here was the stump instead of the perceptron? And at that point, we could glue together with the stump up here and say that, say the H stump with the second degree polynomial feature map is a superset of H axis 2, but we would not be able to say anything about its relationship to H perceptron. Maybe one of the key takeaways from this quiz, one of the takeaways that I hope you all take away is this idea of these are the subset relationships that you are very important, things that I will very likely ask about on your upcoming midterm exam. And this is a tool that you can use if you have to justify something on the midterm exam. Coming back to one of these subset relationships is a great way to justify something. So I would certainly try to say something like this at least once in the midterm exam, and it would not be out of place to say this like 5 or 6 times, something is a subset of something else. Okay. Any questions on the quiz? Anything else about the quiz stuff? Okay, then speaking of the midterm exam, there was sufficient demand for our Friday office hours to be a dedicated review session. So I have just made that the case. And this Friday, 9 a.m. to 11 a.m., dedicated review session, we will, I think, just go ahead and start in the Math Commons room on the 2nd floor of Adams Hall. And so I hope to see many of you there for that. Say it again? The Math Commons room. It's on the east end of the hallway, the far end of the hallway from us here. It's the only room that's not the computer lab that is not an office as well. And the door will be open and there will be a bunch of people in it. So if you walk down the hallway and see a bunch of people in a room, that will be the room. Okay, today in class, we are going to continue talking about this optimization notes right here. And again, as a reminder, this is not going to be on the midterm. This is stuff that will be on your final exam. The midterm will only be about the statistical things from the book that we've covered so far. And then the final exam will be about more statistical things and combining it with this optimization stuff. In the context of machine learning or data mining, optimization is a synonym for the actual algorithm that you are using. And it is how we actually find the empirical risk minimizer, or the G, the hypothesis in our hypothesis class that we are going to actually use to do something. And last time in class, what we talked about was, did all the notes here in under this section 3.3.1, predicting a probability. We didn't actually talk about how to predict a probability, how logistic regression relates to probability. That's something that we're not going to go over in class. You won't be explicitly responsible for, but it is something in the textbook, and it is something that does come up commonly on machine learning interview questions. And so it's worth just reading through that page or two to have been exposed to it once. But what we talked about last time was reviewing about these loss functions, and there's the 3 key important properties that we want a loss function to have. We want it to be a surrogate, we want it to be convex, and we want it to be robust. And the logistic loss gives us as much of those things as we can hope for from a loss function. That's, from an optimization perspective, why we care about the logistic loss. Today in class, we're going to start down here on section 3.3.2 in this gradient descent section of the book. And our goal, the main goal of this, is that there are a handful of plots that look something like this in this gradient descent section. And we want to, our goal today is to basically understand why those plots are what they are and why they're important. The textbook, this is again is one of the weaker aspects of the textbook. They spend relatively little time on this optimization part, and so we will spend more time on that. Most of the things that we will say today are things that are designed to give you a lot of intuition for what's going on, and then we will maybe by the end of today, but definitely next week, start talking about this large-scale machine learning with stochastic gradient descent paper. And this will be more based on where your actual problems for the final exam will be coming from. But this section of the notes, we're again in the notes optimization right here. This section of the notes is more on intuition, getting you comfortable so that the scary mathematical notation is less scary. Any questions on where we're at or where we're going? Okay, then let's dive in and get started. So why is it important to have a convex loss function? We will answer this question by saying what bad thing will happen if we do not have a convex loss function. And the standard example of the non-convex loss function that we care about is the 0, 1 loss. I'll plot this on the z-axis. Z again is equal to y hat times y. And the loss function itself is this step sort of function like this. This is the 0, 1 loss, 0, 1 loss. And this commonly used variable for this loss function when it's plotted like this is the letter q, with z here being the parameter, which again is this y hat times y. The other, and so this is the plot that we took a look at before. The other way of plotting this, another way of plotting this is having the, on the x-axis down here, instead of it being an axis of the z variable, it'll be an axis of the w variable, of the weights of our model. Again, the models, we'll just take a look at remind ourselves the definition here of the perceptron. I'll do it up here. H perceptron equals the x into the sine of w transpose x, where w is contained in r to the d. Here, there's a one-to-one correspondence between the w here, these parameters. One-to-one correspondence between W and the actual hypotheses in the hypothesis class and some sort of H contained in H. And so it's very common for people in the textbook and the paper that we'll be reading to go back and forth between W and H and use them interchangeably. And so down here, one way of thinking about this axis, this line down here, is that it's not only an axis of W, but it's also the particular hypothesis that we are interested in. Another important observation is this y hat up here. This depends on W. Y hat is a function of W. Function of W because y hat equals h of Rx. And again, h and w somehow synonyms of each other. And so this plot up here, this first plot that we were visualizing, is a plot that is somehow a function of w, but we're changing the plot around just a little bit. And so the plot will look similar, but it'll also look a little bit different. Okay, this is this vertical axis 2 over here. This is the 0 location. So I'll add a 0 location right here as well. And when we plot on the axis just on W like this, then it now makes sense, or what we have to consider is the x point as well, the data point. And so we'll say that we have an x right here, and so that x value equals whatever it's equal to, and the corresponding y value will be equal to +1. When we do that, then our 0, 1 loss now gets shifted over and looks something like this. When we are to the left-hand side, when our w is too small, when we're to the left-hand side of this x value over here, then our w transpose x is going to come out as a negative number, and we'll get a negative times a positive, giving us an error of 1. But when the two signs match, we'll come out with a +1 times +1, and so we'll get the an error of 0 over here. This is very rarely visualized with just a single point. This top graph is how it's traditionally visualized with just a single point. But this bottom graph with W here as our x-axis is very commonly used to visualize many points at once. And so I'll redraw this down here now with many points. And I'll label this up here. This is just 1 point. And now with many points. With many points, these x's are going to be all over the place in different locations, and the y's will be not all +1, some will be -1. And when the y is -1, the direction of this plot right here will flip so that there's the high side on the right and the low side on the left. And when you add all of those together, you'll get something that looks like a crazy step sort of thing like this, with many different minima all over the place, and yeah, something like that. This is a very hard to analyze function if you're just sitting at one particular point here. If you have one particular w, it's very difficult to know whether you should go to the left or go to the right to find the minimum of this function. This here, what I plotted, is the E sub n, the in-sample error right here. So this is the thing that we are trying to minimize. It's very hard, though, to know what the minimum is, and we can have a very large range. Like it looks the way I drew this, that this right here is the minimum, and this should be minimum here. So that's where our W star or H star or G is located. But if you're sitting at this point over here, it seems like this is a really good point, and there's no way to know that somehow globally on the other side of the plot, there's an even better spot. So that's the bad thing that happens with the 0, 1 loss. With convex losses and the logistic loss in particular, I'll redraw the logistic loss on top of all these plots now. Everything in red is the 0, 1 loss, and we will use gray here for the logistic loss. The logistic loss has this shape where it is a surrogate of the 0, 1. So again, the surrogate meaning that it is above the 0, 1 loss. And it's also convex, meaning that if you draw a straight line between any 2 points, then that straight line is above the plot in every location. So in the Q plot, this is what the logistic loss looks like on this axis, logistic loss. And in the 1 point plot down here, the way the logistic loss looks is we still just shift that loss over like this. And in the many points case, I'll draw a separate axis now so that it's somewhat visible what's going on. We're going to have an overall convex shape, and I won't draw it centered at 0 like that. I'll draw it so there's a something like that, an overall convex shape like this. And this is again the logistic loss with many points. And now it's very clear where the minimum here is. It's obvious that this is the minimum.
Should the bottom of the convex be where the minimum is, like on the other plot?
The question, that's a good question. I'll repeat it and answer it here in a second. It's obvious, man. The question is, here I drew the minimum of this plot as being kind of close-ish to the minimum of this plot. And the question is that really like the case? I'll write it out in words right here. Is it the case that and I'll do it, this argmin of En logistic should be equal to, or right, approximately equal to the argmin of the En of 0, 1. So these losses up here again, the in-sample error with the appropriate loss function. And the answer is that we have no guarantee about these two things being approximately equal to each other. We have no guarantee that the W value, this again is the W axis right here, no guarantee that this W value that minimizes the logistic loss is in any way correlated with the W value that minimizes the En over here. And what's very likely to happen in practice is that your 0, 1 loss En will have many locations that are very, very close to each other, minimizing the En for the 0, 1 loss. And the logistic loss will pick one of those, not necessarily the best one of those, but one of those and have the minimum close to that. The thing that we do know, though, is because our logistic loss is a surrogate, the En of the En logistic is guaranteed to be greater than or equal to the En of 0, 1. And so by minimizing this logistic loss, we are guaranteeing that the 0, 1 loss will be at least smaller than that. So there's no guarantee on the W, no guarantee that the parameters will be close to each other. But once you plug those parameters into the hypothesis and evaluate that hypothesis on the in-sample test set, there is a guarantee that the results will be at least as good on the 0, 1 loss as on the logistic loss.
So does it matter where we necessarily like visually when explaining it? Like say for the midterm, like I don't know, writing on the logistic curve, like obviously not this kind, but say you were asking a question about this on the exam, like would it matter where we draw the bottom of that curve when we're saying?
Yeah, so the question is about explaining this on the final exam and how does it matter to explain this on the final exam? The answer is that the way this will come up on the final exam is not directly me asking you to do these plots. There'll be some downstream problems that will come up out of this. And the goal of this discussion right here is to get you the intuition for those downstream problems. So the literal answer about like drawing these things, if it did come up, is no, it doesn't matter that how the W's are correlated with each other because there is no relationship to them. But then also the answer is that these particular plots right here, there won't be an expectation that you draw it on the final exam. Okay.
What's the reasoning behind the log loss, like going up again?
Question is here, why is, so it makes sense that the log loss kind of goes down like this on the left-hand side, because over here, the log loss, we drew it like this, where it's high on the left and low on the right. But the question is, why would we ever get it going up again on the right-hand side over here? And the answer is that, let's say, I'm going to, in black over here, adjust this positive one, make that equal to a negative one. Then what that does is it flips the error for both the logistic loss and the 0, 1 loss. The 0, 1 loss now becomes, I'll do the 0, 1 loss in a dotted line like this. This is the L0, 1 with y equals to -1. And then the logistic loss is a surrogate of that looks like this. That's L logistic right here. And so you'll get depending on the data points, whether they were +1 points or -1 points, you'll get the slope going in different directions. The big picture takeaway here, though, is that the logistic loss, the final thing over here, nice, pretty shape, looks easy to optimize, that whatever W you're at, there's an obvious direction to go in order to get towards the minimum. So that is, why is it important to have convex functions? That there's an obvious direction to go in order to get towards the minimum. Problem number 2 down here, visualize gradient descent and stochastic gradient descent. So the paper that we'll be going over next is about some of the math details, the equations behind these two algorithms right here. But this first problem here, just trying to get us some intuition about what these problems do graphically. Let's draw some axes here. This is going to be W on the x-axis down here again. We'll go ahead and keep our 0 point right here. And yeah, we'll still use gray to draw our loss function. This is the in-sample error for the logistic loss, same as it was above. And the question is, so yeah, visualizing gradient descent and stochastic gradient descent. With gradient descent, the picture to have in mind is that you're going to start at some particular point, where how you choose what to start off is usually just to select something at random. But you start at some particular point, this point right here being your W naught. And then you use the gradient of your loss function to determine whether you go left or right to improve your loss function. In this case, the gradient says that we should go left in order to minimize the loss. And so we pick some amount to go left, and we go left by that amount like this. And this right here would be our W1 value. In the textbook, mathematically, what that looks like is their equation for gradient descent is Wt plus 1 is equal to, Wt minus this Greek letter right here is eta times the gradient with respect to W of the in-sample error, E in of Wt. Again, in the past, we have put a particular hypothesis inside of our in-sample error, but this, because there's this bijection, this one-to-one relationship between the W's and the hypothesis, this is equivalent. Anytime we see a W, we can convert it into an H. So this is equivalent to a particular hypothesis right here. You can think of this as like HT being plugged in right here, the H that corresponds to this particular W. And the gradient right here, again, in this one-dimensional case, telling us whether we should be going left or right. And we repeat this several times. And so the W1 takes us here, and then the W2 maybe takes us here. And if we repeat this enough, we'll eventually come down to the smallest point right here. This is a one-dimensional visualization of this formula right here. Another common visualization of this is two-dimension, so we'll do that next. Let's see, for the two-dimensional visualization, there won't be any axes that I will draw. We'll use gray right here. Instead, what I'll be drawing is a bunch of convex shapes that look like this. All of these contour lines are convex, and these are the contour lines of the E in logistic right here. Maybe I said I won't draw axes, but I will actually draw axes down here. So the location of the axes doesn't matter, but the important thing is that we're visualizing the W values as our axis, that this is a two-dimensional problem now, and the thing that we're visualizing here is our our W values. These are contour lines of our EN function right here. So this EN, since the W's are two-dimensional, the EN here is somehow like sticking up out of the page. And this right around here, this would be the smallest best value right here. This dot right here, the smallest value of E sub n. In each of these contour lines, larger values as the distance from the minimum expands. In gradient descent, we pick some particular starting point. We'll say something like this. So this is our W0 point. And then we, using the same formula above, calculate the gradient of whatever your E sub n is right here. And the gradient tells you what direction to go in. In this case, the direction of the gradient right here would look something like this. Notice that it's not taking me directly in the direction of the minimum, that the gradient right here doesn't necessarily point to the minimum, and it's, in the vast majority of cases, it won't point towards the minimum, but it will point in a direction that will take us closer to the minimum. So this W1 value right here, this location right here is closer to the minimum, and so my En at W1 will be smaller than my En at W0. And then at this point, my new gradient might look something like that, taking us to here. And then continuing to iterate this over and over again, eventually getting closer and closer to this minimum point. The formula again for gradient descent, the same no matter what the weight dimensions are down here. It's just a different way of visualizing here. Any questions about these visualizations?
Is the direction in which you're moving orthogonal to where you are?
Question is the direction orthogonal to where I'm at? And the answer is that the contour line, one of the properties of the gradient, is that the gradient projected down onto two dimensions like this will be orthogonal to the contour line itself. It's not actually orthogonal to the curve itself, but this projection of the curve. So yes, all of these orange arrows that I drew are orthogonal to what the contour line is at that point, and that is not an accident.
Is there like a third dimension that's
Exactly, and so sticking up out of the page right here is this En. We're trying to visualize a three-dimensional shape right here, and that's hard to do on a two-dimensional piece of paper, and so we get something that looks like this. I'm going to switch over my screen to some other actual computer renderings of this here for a second, so you can get another visualization of this. And on the left-hand side of here, so these are actual two different machine learning models with different loss functions and the actual resulting curves that you see. These are both recently published papers in ResNet. Here's published 2018-ish timeframe. And so these visualizations, things that people actively care about right now. You will actively see lots of machine learning data mining stuff showing these visualizations. Again, the sort of x-axis here, the dimensions that we're plotting here, these are the W parameters. These models happen to be very, very large dimensional, projected down into two dimensions. And then the vertical axis here is the in-sample error. And on the left-hand side here, you can see something that's very, very non-convex, looks very hard to optimize. And the right-hand side here, it's almost convex, so it's much simpler, easy to optimize, much easier to see how you could go from a random point down here to the middle, whereas on the left-hand side over here, very hard to see how you would do that. So computer rendering, you can do that in 3 dimensions there, but even with computer rendering, it's very common to draw the plots like this with the contour lines. And we'll go down one more. So these are the same plots of that we saw up above. This one right here being a very non-convex shape right here with lots of different local minimas all over the place. The 0-1 loss would look something very ugly like this, and something much nicer like these plots over here. Okay, so that is gradient descent. What I'm going to do next is I'm going to switch our screen here for a second over to this Leon Buteau paper about large-scale machine learning with stochastic gradient descent. The textbook, again, doesn't really talk about the math or details behind gradient descent versus stochastic gradient descent. And so this is going to be our source on those formalisms. And in just a second over here, I'm going to write down the formulas for gradient descent and stochastic gradient descent as they appear in the text in this new reading, and we'll talk about how they can be visualized on those plots. First, maybe things before doing that, though, again, I always like looking at the people who write these things, thinking about who they are and what they're doing. So Leon Buteau, he is this guy right here, currently works at Facebook along with the Vapnik. And so again, if you're interviewing at Facebook, very likely to meet one of these two people in person, or you will definitely meet people who know these people in person and are friends with them. And another fun thing about him is he sometimes likes to philosophize on his personal blog, and a number of people have asked me about over the years here about Borges and AI, and this guy has written a handful of things about that. So I don't know, fun thing about him. This paper that we're looking at, published in 2011, stochastic gradient descent really became super popular in like the 2010 timeframe. That's when Facebook and Google and all of these companies really started gathering large amounts of data. And what we're going to see, what this paper is arguing, is that when you're in this large data regime, lots of data, stochastic gradient descent is the best tool for doing that optimization. Leon Buteau here, he did this particular work at this NEC Labs America. He then was hired by Microsoft Research for 2 or 3 years. I have very few positive things to say about Microsoft. I'm not a big fan of the company, just because of their standard like anti-open source policies about things. But Microsoft Research is something that I very much respect. They are far and away the best industrial research lab in the world, both then and now today. But after working at Microsoft Research, he went over to Facebook in 2015 and has stayed at Facebook since then. Okay, so that's enough high-level thing getting into the meat here. This first part of section 2 right here, all of these equations, this is all of chapter 1 in our textbook, just condensed down into one paragraph right here. And a very standard thing in machine learning data mine papers, there will somewhere be a 1-paragraph summary of chapter 1 in the textbook, just introducing the notation for this paper and how it's different maybe or similar to other notations. For our cases, the main thing that's different is that they use capital F instead of capital H for a hypothesis class. So anytime in this paper you see capital F, think hypothesis class. They also, the reason they use F is they talk about functions instead of hypotheses. So it makes sense to use F, but functions and hypothesis are synonyms for each other. So capital F for the hypothesis class. And then down here, this E sub F with no subscript, this is the out of sample error, what the textbook calls E out. And this E in right here, this is the in sample error, what the textbook calls E in. It's sort of a cute pun that E with the lower subscript letter in is pronounced as E in, the same as E in up here. So this in is the number of data points. That in is the number of data points. And again, just cute notation pun that it pronounced the same as E in sample error. Okay, then 2.1 here talks about their actual formulas for gradient descent, which look very similar to the ones in the textbook. I'm going to switch my screen back over again to the notes packet to talk about these equations and write them out and draw the pictures. So in red up here, this was the textbook's version. And we'll do magenta for the Leon's version. And that looks like WT plus 1 for gradient descent equals WT minus gamma. He uses the letter gamma. This is a gamma Greek letter right here. This is an eta up here. And then explicitly plugs in the 1 over n sum right here for the in sample error and moves the gradient inside gradient W of the Q right here. And I'm out of room. I'll see if I can fit it. Z sub I comma, I can't fit it. So I will, there should be the parentheses, the Z sub I and the W sub T. The I over here that we're indexing on for our data points is the I right here that we're looping over in the summation. And the T over here that is our weight vector, our hypothesis, is the T from our iteration. Both eta and gamma over here, both eta and gamma are real numbers. And these are hyperparameters chosen by the user. So I'll just write hyper right here to indicate it's a hyperparameter, which again means it's something that is chosen by the user. In the same way that alpha was a hyperparameter for the PageRank power method. So both of these are gradient descent. I will abbreviate gradient descent with GD for gradient descent. And the next thing that the paper talks about is something called 2GD, or second order stochastic gradient descent. 2GD. And here what this is WT plus 1 equals WT minus, now there's a capital gamma, this capital letter right here, obviously the capital Greek letter of this thing down here. This is a, yeah, not actually obvious, but this is the capital gamma right here. This is the lowercase gamma Greek letter. And then everything else is the same. 1 over n, sum over I, gradient with respect to W of Q of Z sub I, comma, WT. And in order to think about the implications of why we have a gamma right here, or what this gamma is going to do, we'll need to talk about the shape of this gamma and the shape of the gradient of this Q function. Gamma itself is a matrix, D by D matrix. And our Q loss function, it goes from R to the D into R. So again, the R to the D right here because it takes W as an input and W is an R to the D vector. So I'll annotate that as the input over here is the W, and W has shape R to the D contained in R to the D. So that's why it goes from R to the D into R. The gradient of this gradient with respect to W of Q, the gradient of Q is going to have shape R to the D into R to the D. This is just a general property of gradients in a multidimensional space, is that if you take the gradient of a scalar valued function, you're going to get a vector as the result. And so the output of all of this is a vector. The output of all of this is a vector right here, and it's being multiplied by a matrix over here. The output of this gradient Q is a D-shaped vector, and the matrix over here is a D by D matrix. And so this whole thing right here will have the same shape as our WTs. So that's just a quick type checking thing to verify that this is a reasonable thing to do. Now the question is, why might we want to do this? Essentially what this gamma is doing for us, gamma is going to be calculated from the data. and it is going to give us somehow the optimal value of eta or lowercase gamma. So again, the eta or lowercase gammas, these are hyperparameters selected by the user, and it can be hard to select these things. You can also do somehow an automated system of using this matrix that will select it for you automatically and not have to select it by yourself. In order to see why that's important, I'm going to scroll up here in a second, and we're going to see what are the bad situations that can happen in first order gradient descent and standard gradient descent right here if we select a bad value of eta or gamma. What's the bad thing that can happen? Well, there's two possibilities. One is that our value of eta or gamma is too large. If our value is too large, then we're going to take too big of a step, and we will not only overshoot the minimum right here, but we could even go like so far away that we actually start diverging. So this is what happens when our eta too large. If our eta or again gamma, they're synonyms for each other. If eta or gamma are too large, then we will not converge, will not find the local minimum down here. We will just get an arbitrary W value that sort of expands off to infinity. The other possibility, which is better, but still not good, is if, do it in black, if eta is too small. If eta is too small, then we don't take large enough steps, and so we spend too many times, too many iterations of gradient descent in order to get to the minimum down here. So this black version is eta too small. Revisualizing this in our second plot down here, two-dimensional plot. The black version will look like if eta is too small, we'll get curves that look like this. They'll roughly follow the same shape as the orange one, but not stay exactly on it. This again is too small. And if eta too large, then we'll way overshoot and end up going farther and farther away from our target value each time. So something like this is eta too large. One of the practical difficulties of using gradient descent is, again, selecting this eta or gamma value so that we get into this nice situation where we are approaching the minimum at a good rate and not too small, not too fast. And there's not really good theory on selecting these values. It's just a matter of trial and error, seeing what works or not works. But second order stochastic gradient descent doesn't have that problem. It has this gamma matrix that somehow does that for you. So there's less hyperparameters involved here. The runtime we'll see will be slower because you now have this additional matrix multiplication, but the use of the algorithm will be simpler. Any questions on any of that? Tyler. Yeah, so the question is the only downside of eta being too small that it takes more steps to converge? And that is correct. So if you had an infinite amount of compute for your problem and you didn't want to muck about with trying a whole bunch of different eta gamma values, you could just make eta essentially infinitely small and be guaranteed that after an infinite amount of time, you would hit the minimum value over here. But in practice, we never have an infinite amount of compute. Not even Facebook has an infinite amount of compute. And so the machine learning engineers there do spend quite a bit of time tuning these eta gamma values when they're using gradient descent to get at the minimum faster. Good question.
Couple of questions. One, what does 2 gradient descent represent? Second order.
Yeah, so the question is here, why are we calling this second order gradient descent instead of, and why is this first order gradient descent? It turns out that the optimal way of creating this gamma matrix is by taking a second derivative of Q. So gamma should be equal to, in theory, the second derivative of Q, and then the inverse of that, something like that. A lot of different variations of second order gradient descent that do something sort of like this, but they're all somehow doing some kind of second order derivative down here. And so that's where the second order gradient descent comes from. That's where the name comes from.
And then are the 2 formulas for the first order gradient descent the same?
Yeah, so the question is, what I wrote in red up here and in the magenta down here, are these the same equivalent formulas? And the answer is yes. They're just written in the notation in magenta down here is from the Leon Buteau paper, and the red formula up here is how they write it in the textbook. The main difference here is the Greek letter that they use to represent, sometimes called the step size. I haven't used this word yet. So eta and gamma, both sometimes called the step size, because it determines how large you step on each iteration. Also sometimes called the learning rate. And so they're just, the main takeaway here is they're using a different letter for this same concept. Yeah.
What is that signal on the second gradient order for the 1/n? Is that?
So this thing over here is the gamma matrix, the D by D matrix, and there's a 1/n. This is a sigma right here, the summation, and then the gradient of with respect to W of Q right here.
Yeah, I'm just wondering what the 2 lines signal at the beginning.
This?
No, just the right before the 1/n. Just the,
This.
Is that supposed to be your parentheses?
This is the gamma matrix.
Okay. Oh, I see.
So, and they're using going from the lowercase Greek letter gamma over here to the uppercase Greek letter over here, because it's going from a vector to a matrix. But it's still somehow like representing the same quantity of how far you go each time. Okay. Next time in class, we'll continue with these pictures, talking about how stochastic gradient descent fits into these pictures and equations. And then we will also do a whirlwind tour of the theory of how fast these things converge and see how that lets us choose when to use each algorithm in practice. This is a good stopping point for us for today. Again, Friday, the review session for the midterm. And if you haven't signed up for a midterm time slot yet, make sure that you do that so that, make sure that you do that. If anybody has any questions about anything, I will stick after and get those answered for you about this or the midterm or anything else. Otherwise, have a good Halloween.